You believe you can hold the world in your hands. Every engineer who draws a bridge, every physicist who splits an atom, every general who plans a campaign, they all rest on the same silent faith that nature, at bottom, is a machine, and that machines, if you understand them deeply enough, can be operated. I believed it too. Göttingen in 1926 changed that. When I arrived to study under Max Born and walked straight into the quantum revolution that Heisenberg was building, a revolution that shattered that faith completely. What we discovered there about the uncertainty principle, about the hard limits of prediction and control, changed not only physics, but what it means to act in this world at all. And the thing that shattered it was not philosophy, not theology, not poetry, though all of those had their suspicions. It was the hardest, most rigorously tested science we possess. Quantum mechanics looked into the foundations of matter and found something there that no one was prepared for. Not indifference, not chaos, but something far more unsettling. A fundamental, irreducible limit woven into the fabric of reality itself. Once you understand what that limit really means, not as an abstraction, but as a fact about the world you are sitting in right now, you will never think about control the same way again. Let me take you back to how this actually happened, because the path of the discovery matters as much as the discovery itself. The early 1920s saw the classical picture, the one Newton bequeathed to us, the one that carried humanity through 2 centuries of triumph, begin to crack. Not at the edges where you might expect the unfamiliar to intrude, but at the center. The atom itself refused to behave. Electrons orbiting a nucleus should, by every law of electrodynamics, radiate their energy away and spiral inward to collapse, and yet they did not collapse. Light, which Maxwell had so beautifully described as a continuous wave, struck a metal surface in what we call the photoelectric effect, and ejected electrons one at a time, as though it were a stream of discrete particles, a result Einstein explained by invoking the quantum idea Max Planck had introduced at the turn of the century. And that same light, when passed through 2 narrow slits in the famous double-slit experiment, produced an interference pattern on the far wall, the unmistakable signature of a wave. But placing a detector at the slits to determine which path each photon takes caused the interference pattern to vanish entirely, with each photon arriving as a particle instead. The act of looking changed the result. This wave-particle duality was not a contradiction to be resolved by cleverness, but rather, as Bohr would later insist, a complementarity to be accepted. Even the spectrum of hydrogen, something so simple, a single proton and a single electron, produced lines of light at frequencies that no classical calculation could reproduce. The old physics was not wrong in the way that a guess is wrong. It was wrong in the way that a very good map is wrong. When you discover the territory has a dimension the map simply cannot represent. These were not failures of effort or intelligence. They were signs that the architecture of understanding itself needed to be rebuilt from the foundations. I arrived at Göttingen at 22 years old. Heisenberg had just produced his matrix mechanics, a formulation that dispensed entirely with the visual picture of orbits and replaced it with arrays of numbers representing observable transitions. Schrödinger, almost simultaneously, had written down his wave equation, giving the quantum world what appeared to be a more continuous and familiar description. Dirac was working in Cambridge at the time, finding the deep algebraic structure that unified both approaches. And Born, my teacher, had just proposed the interpretation that shattered the last comfortable assumption anyone was still holding. The wave function, Born argued, does not describe what a particle does. It describes the probability of what it might do. The square of the amplitude gives you a likelihood, and nothing more. This became the heart of what we now call the Copenhagen interpretation, and it remains the standard framework of quantum theory to this day. Consider carefully what that means. The most complete description physics can give you of a physical system is not a prediction, but a spread of possibilities. At the most fundamental level we can probe, the universe does not tell you what will happen, it tells you what might happen, and with what odds. This was not a temporary confusion or a gap in knowledge, waiting to be filled by a more ingenious experimenter. This was the discovery of a boundary. Heisenberg made this precise in 1927, in a paper published in the Zeitschrift für Physik, with what he called the uncertainty principle. The name is slightly misleading because it suggests the limitation lives in the observer, when in fact it lives in nature. What Heisenberg demonstrated was that you cannot, even in principle, simultaneously determine both the exact position and the exact momentum of a particle. The product of the uncertainties has a floor, the constant Planck discovered divided by 4 pi, and no technology, no genius, no act of will can push beneath it. And here is something that most accounts of this principle leave out entirely, which is the deeper point. The familiar illustration, where you shine a photon at an electron and the photon's short wavelength gives you position while its high energy kicks the electron's momentum into uncertainty. That illustration is helpful, but it can mislead you into thinking this is about the clumsiness of measurement. The real truth is structural, and it lives in the mathematics itself. Heisenberg's matrices do not commute. The operator for position multiplied by the operator for momentum does not equal momentum multiplied by position. The order in which you ask questions of nature changes the answers you receive. And that is not a limitation of your instruments. It is an algebraic fact about reality. This is what physicists now call the measurement problem, and it reaches into the very foundations of what we mean by physical knowledge. Bohr, whom I admired more than any physicist of that century, elevated this into his principle of complementarity, the idea that certain pairs of descriptions are both necessary and mutually exclusive. You need both the wave picture and the particle picture to have a complete account of light or matter, but you can never deploy both simultaneously. The universe insists that you choose your question before it gives you an answer, and the question you choose forecloses others. Let me tell you what this does to the classical dream of control. That dream rests on a simple and powerful premise. Know the initial conditions of a system with perfect precision, the position and velocity of every particle. Apply Newton's laws of motion, and you can predict the future state of the system with arbitrary accuracy. Laplace stated this explicitly, claiming that given the positions and momenta of every particle in the universe, he could compute everything that has ever happened and everything that will. That was not hubris in his era. It was the logical consequence of Newtonian mechanics. The universe was a clock, and knowledge was the key to winding it. What Heisenberg's principle does is destroy Laplace's demon at the root. You cannot have the initial conditions, not because they are hidden somewhere waiting for a more powerful telescope or a finer probe, but because they do not exist in the form Laplace required. Nature does not possess simultaneously precise position and momentum for even a single particle, let alone every particle in the cosmos. The program of complete prediction and the complete control that would follow from it is not merely impractical, it is physically incoherent. The universe is not withholding information from you because there is no information there to withhold. Now, in 1982, in a laboratory in Orsay, France, a physicist named Alain Aspect performed an experiment that settled one of the deepest arguments in the history of physics, and the result was unambiguous. It meant that Einstein, the greatest mind of the 20th century, the man whose physical intuition had rebuilt cosmology, was wrong about this. Let me explain what he argued and why Aspect's result proved so devastating. Einstein could not accept that the deepest description of reality was probabilistic, could not accept that, as he put it, God plays dice. He spent years constructing thought experiments designed to expose contradictions in the quantum formalism. Not because he doubted the experimental results, but because he believed there had to be a deeper deterministic layer underneath, hidden variables, a substratum of certainty beneath the quantum probabilities. In 1935, Einstein, along with Podolsky and Rosen, published a paper in the Physical Review that he considered his most incisive attack. They described a situation we now call quantum entanglement. Two particles interact and then fly apart to enormous distances. Measuring the position of one lets quantum mechanics infer the position of the other instantly. Measuring the momentum of the first instead lets you infer the momentum of the second. Because you can choose which measurement to perform, and because the second particle sits too far away to be physically disturbed by your choice, Einstein argued that both quantities must have existed all along. The particle must have carried definite values with it from the moment of separation, and so quantum mechanics, the EPR paper concluded, must be incomplete, with hidden variables lurking beneath. The argument was beautiful and the logic was flawless given its premises, but the premises turned out to be wrong. John Bell, working in 1964, demonstrated that any theory of hidden variables obeying Einstein's requirement of locality, the requirement that distant events cannot influence each other faster than light, would produce correlations between entangled particles bounded by a specific mathematical inequality. Quantum mechanics predicts violations of that inequality, which means the two frameworks make different, testable predictions. And that is exactly what Aspect tested. He measured the polarizations of entangled photon pairs at different angles under conditions designed to close every loophole he could identify, and the correlations violated Bell's inequality decisively and repeatedly. Nature does not contain the hidden clockwork Einstein had hoped for. The indeterminacy is not a veil draped over a deterministic reality. It is the reality. What that means, and the reason it deserves to be said twice, is that this is not a philosophical interpretation, but an experimental result, confirmed dozens of times since, aspect with increasing rigor. The limit on control that quantum mechanics reveals is not a limitation of human ingenuity, it is a structural feature of the physical world. The world is not a mechanism we fail to fully see. It is something stranger, more open, more subtle than any mechanism. Here is what troubled me for much of my life, and what I think should trouble anyone who takes this seriously. We discovered these limits at precisely the same moment in history when our power, our capacity to reshape the physical world, was growing beyond anything our ancestors could have imagined. I stood at the center of that contradiction. The same quantum mechanics that reveals the fundamental limits of prediction gave us the understanding of nuclear structure that made it possible to release the energy bound inside the atomic nucleus. The theory that tells you that you cannot know what a single electron will do next is the same theory that enabled the construction of a device capable of obliterating a city in a flash of light. This is not an irony. It is something more telling. The limits of control and the reach of power are not opposites. They coexist, entangled, if you will forgive the word, in the same physics. When we designed the implosion mechanism at Los Alamos, we were trusting quantum statistical mechanics with the fate of the world. Each individual plutonium fission event was governed by quantum probability. Each neutron captured a roll of nature's dice, and yet the aggregate behavior of 10 to the 23rd atoms obeying those probabilities was reliable enough to stake everything on. The most consequential device in human history was built on the law of large numbers, and that should unsettle you because it still unsettles me. My colleague there, John von Neumann, understood this tension with unusual clarity. He had formalized the mathematics of quantum measurement, the precise description of what happens when a quantum system interacts with an observing apparatus. And then, with characteristic audacity, he turned around and built the mathematical foundations of game theory, the formal science of decision under uncertainty. The same mind produced both, and that was no coincidence. The same insight underlies each. The recognition that the world presents us not with certainties to be exploited, but with probabilities to be navigated. Strategy, whether in physics or in statecraft, is not about eliminating uncertainty, but about acting wisely within it. You can harness quantum phenomena, transistors that exploit quantum tunneling, lasers that depend on stimulated emission, nuclear reactors that channel fission, without being able to predict or control every quantum event within those systems. You work with probabilities, with statistical aggregates, with the law of large numbers that smooths quantum randomness into the apparent determinism of everyday experience. Your table feels solid not because its atoms behave deterministically, but because there are so staggeringly many of them that their collective behavior is overwhelmingly likely to produce the same macroscopic outcome every time you set a glass upon it. And yet the indeterminacy persists underneath everything. There are regimes where it surfaces with full force. In the behavior of individual atoms, in the decay of a single radioactive nucleus, you can predict that half the atoms in a sample of radium, 226, will decay within 1600 years, but you cannot predict which atom will go next or when, not because you lack information, but because the information does not exist until the event occurs. In quantum cryptography, we now deliberately exploit this, because the very impossibility of measuring a quantum state without disturbing it becomes the guarantee that a communication channel has not been intercepted. The limit itself becomes the tool. In the emerging field of quantum computing, we manipulate superpositions and entanglement directly, building machines whose power comes not from overcoming quantum indeterminacy, but from working within its logic. This is what makes quantum mechanics not merely a different theory, but a different kind of theory entirely. Classical physics was a theory of trajectories, where you follow the path, predict the endpoint, and control the destination. Quantum mechanics is a theory of possibilities, governed by amplitudes that interfere and combine, and sometimes cancel in ways that produce sharp outcomes and sometimes irreducible spread. The formalism is extraordinarily precise, confirmed to more decimal places than any theory in human history. And yet what it tells you is that the ambition of total predictive control, the dream that animated physics from Newton through the entire 19th century, was built on an assumption the universe simply does not support. I tried once, in a series of lectures for a general audience, to convey what I thought the implications of all this were. not just for physics, but for how we organize knowledge, for how we think about the open society, for how we understand what it means to live honestly in a world that will not yield its secrets all at once. The open structure of physical knowledge, it seemed to me, was not merely analogous to the open structure of a free society, because both draw from the same source. Both require the acceptance that no single perspective, no single measurement, no single authority can encompass the whole truth. Both demand complementarity, the willingness to hold multiple and sometimes incompatible descriptions, and to recognize that the richness of reality exceeds any single framework. There is a passage in the Bhagavad Gita that I return to more often than I can say, where Krishna tells Arjuna that he has the right to the work, but never to the fruits of the work. After Göttingen, after Los Alamos, after everything, I have come to understand this as something more than spiritual counsel. It is, in a strange and unintended way, a description of our actual relationship to the physical world as quantum mechanics has revealed it. We can act, we can prepare, we can bring all our knowledge and care and ingenuity to bear, but we cannot dictate the outcome with absolute certainty because the world at its deepest level retains a genuine openness that no action of ours can close. And this does not mean that effort is futile, because the opposite is true. Quantum mechanics is the most successful quantitative theory ever constructed, and it is precisely because we understood the limits that we could work within them so effectively. The transistor, which reshaped civilization, exists because we understood quantum tunneling, the fact that a particle has a non-zero probability of passing through a barrier that classical physics says it cannot cross. We did not eliminate the indeterminacy. We designed with it. And we built the modern world not on the illusion of omniscience, but on the discipline of understanding what can and what cannot be known. There is something important in that distinction, and I think it extends well beyond physics. Control in the classical sense, the mastery of every detail, the prediction of every outcome, the elimination of every surprise, is not possible, and the universe has told us so in the most precise language it possesses. But a different kind of engagement with the world is available. One that works with probabilities rather than demanding certainties, one that acknowledges the openness of nature and builds from there, one that replaces the fantasy of total command with something more honest and, I believe, more worthy of us. The desire for absolute control over matter, over outcomes, over the future, rests on a picture of reality that the 20th century proved false. The universe is not a clock, and it is not a machine awaiting a sufficiently knowledgeable operator. It is something more open, more subtle, more unsettling, and more beautiful than any mechanism. The limit quantum mechanics reveals is not a wall that blocks our progress, but a truth about the character of the world we inhabit. And the deepest response to that truth, in physics as in everything else, is not to rage against it, but to understand it, to feel it in your bones, and to build from there. Not from the fantasy of total knowledge, but from the real and humbling and inexhaustible richness of what we can actually learn. That is what the quantum tells us about control. Not that we are helpless, not that knowledge is futile, but that the world's refusal to be fully mastered is not a flaw in the design. It is the design.